All right, we're going to take a look at a Frayer model, which is just a graphic organizer that we're going to use for organizing information about series circuits. So you can see here I've got series circuits in the center, and then I've got four squares surrounding that center. I've got circuit diagrams, equations, example problem, and general facts. And so we're going to be filling this chart in. Just trying to get all of our basic information about series circuits on one sheet of paper. So this is going to act like your notes for series circuits. Now, I am just going to write on blank paper right now, just so that way I can take up more space, because I do sometimes do that. And then you just make sure you are putting this on your Frayer model sheet, whether it's a printout like the one I just showed you or a hand-drawn one. So the first thing we're going to look at are circuit diagrams. And again, this is for series circuit. So with a series circuit, we are going to have our power supply or our battery, and that's just a long line with a short line. And if you remember from previously, the long line represents the positive terminal of the battery, and the short line represents the negative terminal of the battery. So that's just important if we're looking at what direction current is flowing. Then I'm just going to use straight lines to represent the wires. And I'm just going to draw one that's got three resistors in the circuit. So here's one example of a series circuit. And the way we know it's a series circuit is because when the current flows, all of the current is going to go through one resistor, all of the current goes through the second, all of the current goes through the third, and then the current comes back to that negative terminal of the battery where that it gets more energy, and then continues flowing. Okay, so with a series circuit, there's only one path. Here's another way to draw a series circuit with three resistors. I could just draw them all in a row like this, but then I just need to come back around and connect to my battery. So those two are the exact same circuit, just two different ways to draw it out. Let's say I could draw one with maybe just two resistors, and let's say I want to draw one with some light bulbs in it. Okay, we could represent a light bulb with a regular resistor symbol here, or we can also use circles to represent light bulbs. And sometimes people can put little curly cues in there to make them look like incandescent filaments. Or the easy way, if you're not an artist, is to just draw an X through those. And those represent light bulbs specifically. Okay, your generic resistor, little squiggly guy here, could be a resistor, or it could be a light bulb or anything else with resistance in it. And so the main idea here, you're going to want to write this down, is that there is one loop. Okay, so you can think of circuits in terms of loops. So if there is only one loop, it is a series circuit. And one loop means there is one path for current to follow. There's only one choice. Current can't branch, or there's no decision to make. There's only one way to go. That tells you you've got a series circuit. Okay, next thing we're going to do is take a look at our equations. And for our series circuit, we are still going to be using Ohm's law. Okay, and so Ohm's law tells us that our voltage change across the battery, sometimes we'll say voltage drop, that would be voltage drop across the external circuit, or this is the voltage of the battery, that potential difference is going to equal the current that is passing through the battery, or you can think of that as the total current in the circuit, times R, the resistance. And I'm going to put EQ here. That stands for equivalent resistance. That's the equivalent for the whole circuit. Okay, so we might think of this equation as for our whole circuit, or if we want to think about this in terms of an individual resistor, we could say V1 equals I1 times R1. And that would be, again, for an individual resistor. Individual, there we go. Okay, so both equations, Ohm's law, just one is representing the entire circuit altogether, and then the other one can be used for individual resistors. And these could be labeled 1, 2, 3, A, B, C, whatever you happen to have the resistors labeled as. Okay, and this is actually going to be the same. These equations work whether we've got a series circuit, a parallel circuit, you have one resistor in a circuit, whatever. Next, we're going to look at equations that are specific for series circuits. So a special thing about series circuits, since we're in one loop, there's only one place for current to flow. That means that the current flowing through the battery is the exact same amount of current flowing through the first resistor, which is the exact same amount of current flowing through the second resistor, and so on and so forth, okay, for however many resistors or circuit components we have. So the current going through each component of this circuit is identical. Okay, now let's talk about the implication on our voltage. Okay, and we could use the deltas here. I'm actually going to stay away from using the deltas, so meaning change in. It's more technically correct, but it just makes it kind of messy on the page. So these are all supposed to be voltage drops. So this is the voltage of the battery. So if I have a 12-volt battery, this guy would be 12 volts, for example. Okay, and we've learned that the voltage drop across resistor 1 plus the voltage drop across resistor 2, and so on and so forth. We add up the voltage drops across all of the resistors, then that is going to equal the battery voltage. Okay, and the idea here is that, remember, those voltage drops, that really relates to how much energy we're using to get the charges across the resistor. So we've got to get all of the current, all of the charges across resistor 1, all of the charges across resistor 2, all of the charges across resistor 3. So we got to use energy for all of those. Okay, so we add up the voltage drops across each resistor. That is going to get us the total voltage across the battery. Okay, and then lastly, we're going to look at equivalent resistance. And in series circuits, that's pretty easy. So since all of the current has to go through every single resistor, all we do is add up the resistance for every single resistor that's connected in series. And that is going to get us the equivalent resistance. Okay, and this equivalent resistance just means the resistance for the whole circuit. So you may want to write in here that this is equivalent resistance, and that is R for the entire circuit. Okay, and then depending on what you're asked to solve for, or what you know or what you don't know, you're going to use any combination of these equations. Maybe you know all of the individual resistances. You can add them up to get your equivalent resistance. And then you can use that in this Ohm's law equation up here. Maybe you know the voltage of the battery and you've just found the equivalent resistance. Now you can find the current flowing through the battery, which we just learned here is the same amount of current that's going through each resistor. Once you have that information, now we can use our other version of Ohm's law for each individual resistor. We take the current flowing through each individual resistor times the amount of resistance in that individual resistor, and that gets us the voltage for that individual resistor. And of course, there's other ways to solve problems as well, and we will look at some examples of those coming up next.